adder, right? We start talking about adder, a lot of equation. It is pretty messy. But if you want to go into this area, it will be good to have some feeling or even memorize the equation. But for exam, you don't have to would have cheat sheet, right? You can put it here. So last time we say that, yeah, sum is A exclusive of B exclusive of carry in. Okay, and C out is AB plus BC in plus AC carry in, right? This is something fundamental. But then we say, hey, we actually can have more hierarchical approach. With a hierarchical approach, then you have some more insight. We say something called generate. Well, even you don't give me carry in because of the AB, I'm going to generate a carry out. For example, if A and B both equal to 1, or I will propagate. Okay, one of them is 1. Then if your input carry in is 0, I propagate 0. If the carry in is 1, I propagate 1. That's what we mean by propagate. Or delete. If no matter what carry you give me, I'm not going to pass it. I'm going to have 0 carry out. If both A and B are 0, that's why with bar A, bar B, right? With this one, then we can further make C and S carry out and the sum as a function of this generate and propagate. And it's very natural. If you really just go to ask a high school student or even middle school student, you say how to do carry out. Well, this is very natural. This is just a very natural logical statement. What I have carry out, if I generate a carry out, of course, or if you give me a carry in, I propagate it, right? You can write down this equation right away. Of course, when you write it, you need to be careful. If you have the first time, right, you need to make sure in the future you write some new equation. This is a good starting point, but then you verify carefully using the logic, right? And same for the S. And then we talk about the ripple carry adder. If we have a 1-bit adder, it's very naturally we can make many bits, right? Just by cascading. The problem of this easy thing means bad results, right? Everything, if you can do it easily, you really should think what you gain. You probably don't gain much. This is so easy, we cascade them. But then the point is, I need to wait for carry in to do the computation in the last stage. And it takes n-1 stages to propagate the first carry in, or to compute the carry in that is into the last stage. The carry into the last stage, which is Ci3, it is just equal to CO2, right? The output of the stage 2, which is the first stage, is equal to the input to the stage 4, which here we call it the fourth stage, right? Or number 3 stage. So that's why the time is n-1 times T carry. T carry is the time that you use to carry to the next stage. Okay, and then we also have T sum. Later we show that the sum circuit is more complicated because we don't care so much. We want to make it simple, easy to implement, maybe smaller area, right? Because when I'm computing the sum, it takes longer time. That is okay because I'm waiting for it to compute the whole number anyway. Okay, so because of this, sum is longer. So in the last stage, I no longer calculate the T carry. I try to see what is the T sum. So the total delay is n-1 T carry plus T sum. So if we want to optimize, we optimize the T carry because it's multiplied by n-1. Any questions? And then on the right, we show you a circuit of the 1-bit adder. This is complicated. We discussed many things. Please go back to look at that. Then we understand why we want to put the carry in signal at the output, why we simplify in this way. And in particular, remember that we actually compute the carry out bar first. This is carry out bar, CO bar, and then use this to help us to compute the sum, to save some of the area, but it will take a longer time. But that is okay again, because T sum, which is from here to here, can be longer than T carry, okay? So if no question, I will continue just to review again about this mirror adder, that is kind of review. So make you, I think maybe you forget. Basically, do you remember what is a mirror adder? Anyone have any reminiscence, any memory on what we discussed last time? Why mirror adder is so special? I show you an adder here already, but why mirror adder looks a little bit special?
Is it because you got rid of that intermediary inverter as well as the stacking?
Actually, here we actually skip it. You see, this is carry out, right? So actually, the real
it's
carry
there.
in, yeah, it is still, we still need it, but we did not draw it.
Got it. Okay.
Yes, but that's a good point. What's so special? Remember, what's the meaning of mirror? Remember that for the same logic function, usually the pull down network and pull up network are not the same. If it is len in the pull down network, it becomes nor, or I should say, if it is parallel in the pull down network, it becomes series in the pull up network, right? But here somehow they are the same. Series still series, parallel still parallel, and then series still series. That is because we use the inverting properties of the adder. What is the inverting property? It tells us that if I have the C in here, A, B, S, C out, this is exactly the same as if I take all the knots to this terminal, C in, A, B, C out, S. This is just, it happened that adder has this property. Addition has this special property. And because of that, you will be able to derive this, which we did not derive here, right? But by doing so, they become symmetric in terms of the layout. And the good thing is that now we only have 2 transistor stacking. If you compare to the previous adder, we have 1, 2, 3, right? We're stacking 3 transistors, but now we only have 2. Okay. And also we apply the C in directly to, this is the same. I just C in is at the output of the gate, yeah, which is the critical signal. Okay. But that is just a mirror adder. But most important, it also has some special property. For example, this is generate. You can see that if A and B are both 1, this becomes 0. No matter what happened to CI, this will be 1. So the output will be 0. I write the wrong thing. Sorry, there should be no bar, right? We did the inverter. Yeah, that's not a bar. That actually was the wire I tried to write. Okay. And then you also have Q, 1 propagates and 0 propagates. So with this one, it will be easier to understand the structure, right? So as I said, many people use this for the project. Any questions? If no, let's do again carry bypass, because we need to make sure that what we have learned before, otherwise you might get lost. So we say the carry take a long time to propagate. Can we compute the carry first? Indeed, we can, right? So we say that we will generate the G, right? This is a review. We already wrote that last time. G equals to A and B. It will generate and propagate equals to A. Can someone tell me what is propagate?
A or B, A or B.
Exclusive or B, right? Only one of them is 1, then you will propagate, right? So we did spend some time. For example, here is G, right? We did spend some extra resources, including to have the AND gate, right, to the G, and then to generate the G and P. So extra area, extra delay. We can call this a setup time, T setup, right? But it's useful. Why? On the top is not useful, right? But on the bottom, we say that, hey, I can just route. If I treat this as a block, I route this one to here. And then if P0, P1, P2, P3 are both 1, it means that this one will propagate this one. So if this one propagate, it means it is here, right? And this one will propagate this one, so it is here, right? So I know that eventually it will propagate. Then why do I want to wait for this to compute? I will just use a multiplexer and select this 1. This is 1, this is 0, and copy it. Then I don't need to wait for this one to compute. I can have this ready for the next stage. Then when you are computing, my next stage will start computing also, right? For example, here, generate, I asked you last time already, what is generate in this case? If A is all 0, B is all 1, what is generate? What is G in this case? When I say this, I basically say what is G3, G2, G1, G0. What are they?
4 zeros.
4 zeros. Thanks for answering, right? And for propagate, we have P3, P2, P1, P0. What are they?
4 ones.
Thank you. 4 ones, right? So because there's 4 ones, so in this particular case, it means BP equal to 1. So it's going to select the signal directly. Okay, any questions? Now, if no, then that's why we try to look at the delay, right? So again, what happened? First, you set up, everyone set up. We don't depend on the others. So all the 16-bit get set up. In this particular case, capital M equal to 4 bits. We put it into 4 bits, right? So we need a setup time of T setup. Okay. And after that, what happened? Then, well, this one will start propagating to the next stage, right? So first of all of them will start computing. Okay, so this will take M T carry. This is just a ripple carry adder, right? Okay, and same for this one. This one will start computing. However, this one will only start computing when this one will bring in the data, right? So you need to wait for 1, 2, 3. N divided by M in this particular case is 16 divided by 4 minus 1, right? This is 4. T bypass, right? So that this one will be valid to start computing. Okay, and then after that, of course, here each of these has a T bypass. This one T bypass, right? So we have 3 of them, and then here we also need to go through the ripple carry, but this is just a regular ripple carry. So you see that a regular ripple carry will have M bit, right? So M minus 1 T carry plus the T sum, just like here. We have N minus 1 T carry plus T sum. This is the last block. Now, with this, then you see that, of course, T bypass is just a regular multiplexer. It is easy, right? This is very short. So it's still dominated by this T carry, right? However, T carry now is only 4. So it is much faster. Any questions? Now, so if you compare the carry bypass adder compared to ripple adder, right? Ripple adder is in the speed of what? This is the slope, right? Proportional to n, right? It's almost 1. I should say this slope is almost 1. Okay. And how about this slope? This slope is smaller, m divided by n. Okay, so for the bypass adder, you take the increase in the delay is slower when you increase the number of bits. But at the beginning, it is bad if you only have a very few bits. Can someone tell me why I have more time compared to ripple adder when I use bypass adder? Which I also just mentioned. Right, when I have 128 bits, I definitely gain a lot by using bypass adder. But when I only have 1 to 4 bits, I don't get a lot of gain, and actually I'm slower. Why is that? I can show you the figure one more time. Do you see why?
Is it because T-sum?
Because of T-sum. Let's take a look. I also have a T-sum here for the ripple carry, right? For ripple carry, I have n-1 T carry and then plus T-sum. Here, I also have this T-sum, right? Of course, now I only have n-1 maybe times 2 T carry. I have 2 of them, should be 2, right? But what I'm saying is that when the n is small, this one is worse than the ripple. Why? So you can compare what are the extra delay you have when you use carry bypass that did not happen in ripple carry. Right, in ripple carry, I have the T carry, I have T-sum. What do I don't have in ripple carry?
T bypass.
T bypass, and also remember setup. Yes, this is thanks for answering, right? This one come to here, it becomes P3 and G3. In ripple carry, we don't need P3 and G3. Why do I need P3? Because I need the P3 to do the selector, to select this one, BP, for the product of every propagate, right? So when there is a small bit, when n is small, you have first T bypass, which is the multiplexer that slow you down. And also you have the T setup. Okay, that slow you down, right? So you see that it's only beneficial if you go to very high number. I think this should be 2m divided by 2 by n, because we have 2m, right? Because we need to do here. Remember, when I do this one, everyone is running. Okay. This one cannot run yet because it depends on the carry from before, and it can be dependent on this one, right? Okay, any questions? So we can move to something more complicated. So we need to understand this well before we can move forward. Any questions? This one always confused me, actually, right? So why I can, for example, you might have question, isn't that this one need to rely on this input, right? But this input, what if it depends on this input? Isn't that this one will need to wait for this computation, right? So the reason is that if this one is just propagation, right, you will just take this directly, right? And if this one will generate, depends on this one, then it means this one does not depend on this one. So this one will start, but this one also start. They just do it at the same time because this one is either generate or delete. This one does not depend on this one. So this one, so you always will have one that will start, right? So if this one depends, on this one, then it will just go through here. Okay. Maybe I make you more confused, but think about what I'm talking about. Okay, why we can have this bypass without problem. But the main point is you always have one here and one here, or you have two. It can be at any places. Here we assume that this one here, but they are computing in parallel. Okay, so you have two empty carry. Okay, now if no question.